Weather is the atmosphere's condition at a particular place and moment. It is what you feel when you step outside, the heat on your skin, the dampness in the air, the direction of the wind, the thickness of the clouds, or the first drops of rain. But those familiar experiences are only the surface of a larger system. Weather is usually described with measurements like temperature, humidity, pressure, cloud cover, wind, precipitation, and atmospheric stability. Each of these measurements affects the others. Warm air can hold more water vapor. Moist air can form clouds when it rises and cools. Pressure differences create wind. Clouds can change how much sunlight reaches the ground. So weather is not one isolated event. It is the visible behavior of a constantly moving atmosphere. Most of Earth's weather happens in the troposphere, the lowest layer of the atmosphere. This layer begins at the surface and reaches upward for several miles, though its height changes with latitude and season. The troposphere matters because it is directly connected to the ground and oceans. Sunlight warms Earth's surface, and the surface then transfers heat to the air above it. Water evaporates from oceans, lakes, soil, and plants, feeding moisture into the air. Winds mix this air, lift it, and move it across regions. Above the troposphere is the more stable stratosphere, which acts like a boundary above much of this turbulence. In practical terms, the troposphere is the planet's weather workshop. Clouds form there, storms organize there, and daily conditions are constantly rebuilt there. Weather and climate are closely related, but they are not the same thing. Weather is short-term. It tells you what is happening today, tonight, tomorrow, or next week. Climate is the long-term average of atmospheric conditions over years or decades. A place with a dry climate can still have a rainy day. A cold region can still experience an unusually warm week. This distinction is important because weather is variable and noisy, while climate describes the background pattern that makes certain kinds of weather more or less likely. Weather is like one frame in a film. Climate is the character of the whole film over time. A single frame can look surprising, but it does not erase the larger pattern. At the same time, changes in climate can shift the range of weather that people experience. The main engine behind weather is uneven heating from the sun. Earth is round, so sunlight does not strike every part of the planet at the same angle. Near the equator, the sun's energy arrives more directly and is concentrated over a smaller area. Near the poles, the same energy is spread across a wider surface and passes through more atmosphere. This creates a strong temperature contrast between tropical and polar regions. Earth's tilted axis adds seasons, because each hemisphere receives more or less direct sunlight at different times of year. These differences in solar heating create differences in temperature, pressure, and moisture. The atmosphere responds by moving. In a basic sense, weather is the atmosphere's attempt to redistribute energy across an unevenly heated planet. Pressure differences turn heating into motion. When air warms, it generally becomes less dense and tends to rise. When air cools, it becomes denser and tends to sink. Rising and sinking air create regions of lower and higher pressure near the surface. Wind forms as air moves in response to those pressure differences, though Earth's rotation bends that motion and makes real wind patterns more complex than a straight line from high to low pressure. Moisture adds power to the system. When water vapor condenses into cloud droplets, it releases heat, and that heat can strengthen rising motion. This is one reason thunderstorms can intensify quickly when warm, moist air is lifted into an unstable atmosphere. Pressure, heat, and moisture together create the motion behind many daily weather changes. On the largest scale, the atmosphere organizes into broad circulation cells. In the tropics, warm air rises near the equator, spreads poleward high in the atmosphere, and sinks in the subtropics. This circulation is known as the Hadley cell, and it helps explain why many deserts sit around 30 degrees latitude. Sinking air warms and dries, suppressing clouds and rainfall. Farther north and south, the Ferrel cells and polar cells help complete the global circulation pattern. These cells are not perfect or static, because continents, oceans, mountains, and seasons disrupt them. Still, they provide a framework for understanding why some regions are usually wet, others are dry, and storm tracks tend to follow certain paths. Local weather often begins with global circulation. In the middle latitudes, one of the most important features is the jet stream. A jet stream is a fast-moving river of air high in the atmosphere, shaped by sharp temperature contrasts between cold polar air and warmer subtropical air. It does not flow as a simple circle around the planet. It bends into waves, and those waves can steer storm systems, guide cold air outbreaks, and influence heat waves. When the jet stream is strong and active, weather can change quickly as systems move through. When it becomes stuck in a persistent pattern, one region may stay wet for days while another remains unusually dry or hot. Many large mid-latitude storms develop from instabilities connected to this high-altitude flow. The jet stream is like a steering current for much of everyday weather. Clouds and precipitation form when moist air cools enough for water vapor to condense. This often happens when air rises. Air can be lifted by surface heating, by mountains, by a weather front, or by the circulation around a storm. As air rises into lower pressure, it expands and cools. If it cools to its saturation point, water vapor begins collecting into tiny droplets or ice crystals around small particles in the air. Those droplets and crystals become clouds. Precipitation forms when they grow heavy enough to fall, or when ice processes inside clouds create snowflakes, hail, or raindrops. What looks like a simple shower is actually a chain of events: evaporation, transport, uplift, cooling, condensation, growth, and descent back to the surface. Altitude and landscape shape weather in powerful ways. In the troposphere, temperature usually decreases with height, which is why mountains are often cooler than nearby lowlands. Mountains can force air upward, causing it to cool and form clouds or precipitation on the windward side. On the opposite side, descending air can warm and dry, creating a rain shadow. Oceans also matter because they heat and cool more slowly than land, moderating nearby temperatures and supplying moisture to the atmosphere. Cities can trap heat through pavement, buildings, and reduced vegetation, creating local heat islands. Forests, deserts, snowfields, farms, and coastlines all exchange heat and moisture differently with the air above them. Weather is planetary in its drivers, but local geography decides how those drivers are felt. Weather forecasting is the scientific attempt to predict a chaotic system. Meteorologists use observations from satellites, radar, weather stations, balloons, aircraft, ships, buoys, and other instruments. Computer models then use physics to estimate how temperature, pressure, moisture, and wind will evolve. The difficulty is that the atmosphere is sensitive to small changes. A tiny difference in the starting state can grow into a large difference days later. This is why forecasts are usually more reliable for the next few hours or days than for far into the future. Forecasters also use ensembles, which run models many times with slightly different starting conditions. Instead of pretending the future is certain, ensemble forecasting shows a range of possible outcomes and helps estimate risk. The chaotic nature of weather does not mean it is random. The atmosphere follows physical laws, but it contains so many interacting parts that perfect prediction is impossible. A small change in temperature, moisture, or wind in one place can influence how a storm forms somewhere else. This is why weather prediction improves with better data and stronger computers, but still has limits. Forecasts are best understood as informed probabilities, not guarantees. A 40% chance of rain does not mean the forecast failed if rain does or does not happen in your exact location. It means the atmosphere supports a certain likelihood under the current evidence. Good forecasting combines equations, observation, probability, and human interpretation. It is one of the most practical examples of science working under uncertainty. Humans have tried to influence weather for centuries, but direct control remains extremely difficult. The atmosphere is too large, too energetic, and too interconnected to command in a simple way. Techniques like cloud seeding may affect precipitation under specific conditions, but they do not allow people to reliably steer major storms or manufacture weather at will. At the same time, human activity has changed the broader environment in which weather happens. Agriculture alters land surfaces and moisture exchange. Cities change local heat and airflow. Industry has changed the composition of the atmosphere, affecting climate, which in turn shifts the background conditions for weather. The result is a strange contrast. We cannot easily control tomorrow's storm, but we have become capable of influencing long-term atmospheric patterns. Weather is not limited to Earth. Other planets with atmospheres also have winds, storms, temperature contrasts, and circulation patterns. Jupiter's Great Red Spot is a famous example, a massive anticyclonic storm that has existed for centuries. Studying weather on other worlds helps scientists understand which atmospheric behaviors are universal and which depend on Earth's special features, such as oceans, continents, life, and a relatively moderate atmosphere. Even the Sun produces space weather. Its corona constantly releases charged particles into space, creating the solar wind, which flows through the solar system and can interact with planetary magnetic fields. Seen from this larger perspective, weather is matter and energy in motion. On Earth, it shapes daily life. Across the solar system, it reveals that atmospheres and stars are dynamic, restless systems. If you found this helpful, please like this video and subscribe for more explainers.